This video is going to talk about Newton's method, which is a method to approximate a zero or an x-intercept of a function, or maybe there's not, a nice algebraic solution here. So I've already kind of drawn right here what our goal is. So our goal is to be able to find that zero. So here's how this process is going to work. We are going to start with an initial guess, which you may say, why would I start so far away? But just for purposes of drawing, suppose that this is x sub 1 right here. So this is our first guess. So that's x sub 1. All right, so now what we do is we take that first guess and we take it up to the function. So right here on the function, we would have the point x1, and then if this is f of x, this would be, of course, just f of x1. And then we find the tangent line, the equation of that tangent line, and then we're going to take that all the way down to its x-intercept, or its 0, and that is going to be our x sub 2. But first, let's find the equation of that tangent line. So we're going to go back to our linearization that we had back at the beginning of this section. So this has been useful in differentials and now in Newton's method as well. All right, so if you remember, your linearization, essentially your equation of the tangent line, starts off and says, okay, it's going to be whatever the slope is, which is going to be f prime at this specified point of x sub 1, and then times the quantity of x minus, and then that little x coordinate there. So now we're going to be, so let's say, okay, so this is our x1, f of x1 point. All right, so x minus x1, and then close parentheses, and plus adding over our f of x sub 1. So it's just like adding that y coordinate over. So that was our linearization. Now what we want to do is we want to find the 0 or the x-intercept of that. So what we do after we find this tangent line is then we want to take that tangent line all the way until it hits the x-axis, and that is going to be our second guess. So this is going to be our x sub 2. So we need to find the 0 of that tangent line. Okay, so the next thing we're going to do is we are going to find the 0, or if you prefer, x-intercept, same exact thing, of this tangent line. All right, so how do we find x-intercepts? How do we find zeros? Well, you sub in 0 for y and you solve for x. So that's exactly what we're going to do here. We're subbing in 0 for the whole output, and then we have, f prime of x sub 1 times x minus x sub 1 plus f of x sub 1. And then my goal, of course, here is going to be to solve for this x right here. And that is going to end up being my x sub 2. All right, so just doing some, basic algebra here as we do our solving. We would probably first just subtract over, so here, just subtracting over our f of x1, so just moving that over to the other side. So we have our minus f of x sub 1 equals the f prime of x sub 1 times the quantity of x minus x sub 1. Again, this x, let's keep in mind, that's the one I'm going for to solve. All right, so probably the next thing I would do would be to divide by that coefficient of the f prime of x sub 1. So we're going to divide both sides by the f prime of x sub 1. And so now we have this minus f of x sub 1 divided by f prime of x sub 1, and that is equal to our x minus x sub 1. And again, our goal is solving for that x. And so our last step here would be to add this x sub 2 over to the, x sub 1, excuse me. So we're going to add that x sub 1 over to the other side. And so what we now have is that this x, that's been my goal to solve for, so this is going to be the 0 or the x-intercept over here. Okay, that is equal to, we just added over the x sub 1 and then minus the f of x sub 1 divided by the f prime of x sub 1 that was already there. That is now our next guess, is this x-intercept. So in some ways I've already written all this work here. So this is, so our x sub 2, so I'll just say this implies that this x sub 2 from all this work up above, that was the x-intercept of that tangent line. So our x sub 2 is equal to this x1 minus the f of x1 divided by the f prime of x1. I think this is actually where I left that space to do that work. Okay, so yeah, that's where I left that space. Okay, so here's where we're at. I'm just restating this again. But this is the algorithm. Okay, so now when you want to get to kind of the next guess, it's going to be the previous guess minus f of that previous guess divided by f prime of that previous guess. All right, so this was, if we kind of continue the pattern, so right here, this was our x sub 2. And so just like before, we take that guess and we travel now to the function. And then we look at, well, what would its tangent line look like? And then kind of graphically what we're doing is we're following that tangent line down to its x-intercept. And that now becomes our next guess. So this is going to be my x sub 3. And so on. So we're already so close here to try to draw in a tangent line. Right? That's kind of why we had to start far away, is that we couldn't even hardly see it at this point. It would be indistinguishable. So this is the general pattern right here. So x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. And what we hope happens is what we were just seeing visually, is that the sequence of these x sub i's converges or is closing in on, getting closer and closer to the 0. So these are our steps for Newton's method. We're going to start with either a given value, or we may make a first guess like using our graphing calculator that's close, reasonably speaking, to the 0 we're trying to find. And then everything is based on this iterative formula right here. This is our formula for Newton's method. And so the key here is going to be doing this effectively and efficiently in our graphing calculator. Okay, so once again, this is your formula for Newton's method. And we keep going until typically you get agreement to a certain number of decimal places. So that's the formula behind Newton's method. So let's take a look at one example, and then we'll come back and do more next time. So estimate the real solution of x cubed plus 3x plus 1 equals 0, starting with x sub 1 equals 1, accurate to the thousandths place here. All right, so the things I'm going to need in this process is, of course, the f here is the function that I'm trying to find the 0 for, or the solution, the real solution. So this is my f of x. And that, of course, means the other key piece we need is the f prime of x. And so that's our 3x squared plus 3. And so if we look at the first x sub 1, we're told to start at 1. So now going on to the next guess. So x sub 2 is going to be the previous guess minus f of that previous guess, so f of 1, and then divided by f prime of that previous guess. So f prime at 1. So, I mean, certainly we could do like one of these by hand, right? We'd have 1 minus, if I sub in 1 into f, I would have 5. If I sub 1 into f prime, I get 6. So 1 minus 5/6 would be 1/6. So this is my x sub 2. Now, we start to get into something like this. Of course, what would the next one look like? I mean, we can write it out. But what happens is we really want to be able to use our calculator in a really efficient way, because very quickly we're going to get numbers that are going to be kind of cumbersome in terms of subbing those in. So this is the mathematics of what we're going to do. Now let's let our calculator kind of do the heavy lifting on this. All right, so let's go ahead and take a look at bringing up our graphing calculator here. So let's go into our y equals, and it looks like I still have a couple of things in here from last time we used it on a video. I'm going to clear those out. So here's what I'm going to do. I am going to always store f. I am going to store this into y1, and then I'm always going to store my f prime into y2 in my calculator. So into y1 is going to be x cubed, and then plus 3x plus 1. And into y2 is the derivative, so 3x squared plus 3. Okay, so those are in there. Now, let's go back to the main menu, so second quit. And so the first thing I'm going to type in is just the first guess, which is number 1, and then I'm just going to hit enter. Now what we're going to do is we're going to call up, so we're going to redo x sub 2 here. So we're going to call up that second, the little negative button is the last answer, minus, and now you want to go into your variables menu, vars, arrow to the right to y vars, y variables, hit enter on number 1 on the function, and then number 1 for y1, that's like f. Now, your calculator understands function notation, so you type a left parenthesis, and then again, second, and that answer feature, and then close parentheses. So just like you would do f of answer, f of value, you can do y1 of value, divided by, and now we want to do that for y2 because that's my f prime. So again, the vars menu, arrow to the right to y variables, 1 on function, and this time 2 for y2. Again, left parenthesis above the 8 there, second answer, and then right parenthesis above the 9. That's the full sequence, hit enter, and that of course is our decimal approximation of 1/6. Now, the beauty of doing this one time is you can now just hit enter. And, or, well, most of your graphing calculators you can. It looks like on this app I'm going to have to say second enter, because that calls up the previous entry. So if I do second entry, that calls up that whole last line that I had typed in, and that's what I want to do again based on this new answer. So that's perfect, and I hit enter. So this is now giving me, my next result is going to be negative 0.321 repeated, and then we're going to continue this. So my x sub 4, so again, you can do, on your calculator, you should be able just to hit enter, but on this one I have to do second entry, which is fine. And then we hit enter. So the next x sub 4 is negative 0.322. I'll write out 1855723. And one more time, let's do it. So this is going to take us to x sub 5 and second entry. So this is the power of using our calculator effectively. So negative 0.322185 and so on. So in this problem, we were told accuracy to the nearest thousandth. So that means we need agreement to 3 decimal places. So I didn't yet have agreement to 3 decimal places when I was at x3 to x4, because that was 0.321 and then negative 0.322. But now between x4 and x5, I definitely have accuracy, agreement, let's say, to 3 decimals. And in fact, I could actually say, looking at what we have here, we could actually say that our real solution is approximately negative 0.322, and we actually have agreement out a few more decimals, 185. So we only had to get agreement to 3 decimals, but hey, for free, we ended up with agreement to 6 decimals. Okay, so that's how we can do Newton's method pretty efficiently with our graphing calculator. We'll look at another example of this next time.